Hi everyone. So this is activity 1.7. So this activity we're going to learn about, in last activity in 1.6 you learned about finding the average rate of change. And then this one we're going to start talking specifically about linear functions, what their intercepts mean, what it means for their slope, and how to find zeros of linear functions. So we start off with a situation where you're buying a car. But as every car does, this Honda is depreciating at $1,750 a year, starting out at $20,905. So I already filled in the table, just plugging in. If I've owned it 0 years, I still have $20,905 in value, and then it goes down $1,750 per year. So I just filled that in ahead of time. Okay, so let's go through some of the questions. So is the value of the car a function of the number of years owned? Okay, so we would say, we're looking at that table. For each input, there's only one output. So yes, this is a function. Okay, each input corresponds to one output. Okay, what's the input? So the input in this case would be number of years owned. That's our N. And the output would be the value after that number of years. So that's our V. Okay, and soon we'll be calling that V of X or V of N. Okay, so let's take any two ordered pairs from that table and find the average rate of change. So average rate of change is really just finding. So if I take just the first two ordered pairs, the way I kind of do it is I say, okay, from there to there, from those 2 points, it goes down 1750, and that's a change of 1 year. Okay, so my average rate of change would be negative 1750 over the course of 1 year. Okay, so this would be negative $1,750 per year. Oops, that's what they wanted right there. So this would be dollars per year. Okay, so what's the practical meaning of this? So this average rate of change is really meaning that this car depreciates that many dollars every single year. Well, we're going to figure out if it's consistent. So it depreciates $1,750 per year. Okay, so now we're going to do the same thing with two other points. So what I'm going to do is I'm going to do the same thing right here. I'm going to go now from here to here and here to here. Doesn't matter what two ordered pairs. So if I do the same difference, if I find the difference from 17,405 and that 15,655, it is decreasing. It's going down 1750 again per 1 year. Okay, so same thing, 1750 per 1 year. Okay, so select two more ordered pairs not used. If I use another two set of ordered pairs, that's going to be the same thing. Okay, it's going to keep reducing to the exact same amount. Okay, so if I take another set of ordered pairs, I'll end up getting negative 1750 per year. Okay, so in the last activity, this didn't always happen. It did a couple times, but not always. It was not a consistent average rate of change. With the one with the weight loss, you went up a little, you went down a little, so it was not consistent. So here, the average rate of change is staying the same. So it remains the same. So no matter what two ordered pairs we have, we're getting the same rate of change. Okay, so what is this? Flip to the next page. I already have a graph there, but let's go up to the top. Okay, so if that happens, what it means is that if I have the same rate of change between any 2 points, it means I have a linear function. It means that when I graph it, okay, I'm just going to add this in here, this forms a line. Okay, a line is where the average rate of change between any 2 points is the same thing, and that's what makes it end up being a straight line. Okay, so next question, is the value of of the car a linear function? And we would say yes, because what we just found, that the value is changing consistently with the number of years we own. So yes, because the average rate of change stays the same. Between any 2 years that I own it, I'm losing the same amount. Okay, I'm losing this $17.50. So is it increasing or decreasing or constant? So an increasing would be something like if you have a bank account and you're putting the same amount of money in every single month and it's going up by the same amount. That would be an increasing linear function. But this one's decreasing, okay, because I'm losing money. I'm losing value in the car every year. A constant would be, my best example for a constant function would be like if you had a phone plan that had unlimited everything. So your bill was constant. Your bill is the same no matter what how much time you spend on the phone, text, things like that. So those unlimited plans, those would be constant functions because your bill is going to stay the same. Okay, so the next part is to graph those ordered pairs. So I just did that ahead of time just to save a little bit of time in the video. Okay, so what you'll want to do is maybe stop the video, graph your ordered pairs, and just make sure you're getting the same graph that I have right here. Okay, so now we start talking. We introduce this new term. I'm sure it's not new to you, but in this book is the first time they're calling this now slope. It's actually better that you think of it as, oops, sorry about that, as rate of change, because that's what slope is. We get slope stuck in our head to be rise over run or changing y over changing x, but what it really is, it's a rate of change. It's how fast the line it goes up or how fast it goes down. So you want to think of it as a rate. Dollars per year or miles per hour, those are slopes. Okay, so but here's what we really did on that table before. Okay, we did subtract the y's and we did subtract the x's to figure out how many dollars it depreciated per year. So there is the formula still there. Okay, so what is the slope of the line graphed in that problem? Well, if I went and found the slope and changing y and changing x, which I already did, we're going to find that it's negative 1750 over 1, which I don't really need the 1 here, but I'm just trying to show that it's per 1 year. Okay, so it really just, I would write it as negative 1750. Okay, what's the relationship between slope and the average rate of change? They're the exact same thing. They mean the same thing. Okay, slope is when you have a slope when you have a constant rate of change, when the rate of change stays the same all the time throughout the line. So what's the practical meaning of slope here is that the value of the car goes down. That's why it's negative. 1750 per year. Okay, so now we're going to start talking about two intercepts. Okay, and you'll see how these all kind of relate together. But this isn't the first time we've looked at an intercept, but a vertical intercept and a y-intercept. Okay, they mean the same thing. So they use two different names for them. So the vertical intercept is where the function crosses the vertical axis or the y-axis. So if you look back at your graph, I'm not going to flip back slides because I think this is when the videos kind of get messed up, so I'm not going to flip back. But if you look back at the graph you did in the previous page, you'll see it crosses the y-axis at the point 0. No, I guess I need to grab that number. I think it's 20,905. Okay, this is my x, this is my y, or input output. So that was our starting value. That vertical intercept is the initial value of the car. Really when n equals 0. So whenever you have an intercept, either a vertical or horizontal, something is 0. So if I'm looking at a vertical intercept, it means my input was 0. And then we'll look at the opposite in a second. Okay, so now we're starting to kind of put the slope and the intercept together. Okay, So now they want us to write an equation, really a symbolic equation for the value of the car for any number of years. We actually could have done this at the beginning, but so if I wanted to find the value after any number of years, I would take my starting value, which is at 20,905, and I would take off 1750 for every year that's gone by. So that's really a symbolic equation. So what we looked at in the page before was the graph of that symbolic equation. Okay, so if you graph this on the graphing calculator and use the windows that they tell you, you're going to have the same exact graph as you did by hand. I mean, one is just doing it by hand, one is doing it on the calculator. So in this equation, what we want to look at is what each of these numbers are. So right there and right there, we've got two numbers, okay? So this one right here is our slope. Okay, the slope is always attached to the input because it's a rate. Okay, it's 1750 per year, per n that goes by. And then this right here, that's our vertical intercept. Or in other words, our y-intercept. Okay, so that's kind of what we just, for number 8, we just answered that. Our slope is what's in front of the variable. Okay, it's what's being multiplied by the variable. It's not always in back, it's not always in front, but it's the one that's attached to the variable. And then the y-intercept is the one that's the constant without the variable. That's the starting value. Okay, so here you see now we're kind of putting it together. Whoops. Okay, so when you have it in this form, you see something that's linear can be written in mx plus b or b plus mx. They're the same thing. Both of them have the m attached to the x, and the b is not attached to the variable as the y-intercept. So that's what we call slope-intercept form. So in the next couple activities, you'll talk about two different forms, slope-intercept form, and then you'll start talking about standard form as well. So I'm going to do just a couple of these. Down here, we've got a couple equations, and they're asking us to pick out slope and a y-intercept or vertical intercept. So I'm going to write this, instead of using symbols, I'm just going to write, whoops. Okay, so for this one, my slope would be -2. Okay, which if I was graphing, that means I would go down 2 for every 1 over, down 2 for every 1 over. And my y-intercept is 5, but as an ordered, I'm going to write it as an ordered pair. It's really 0, 5. That's where it crossed the y-axis. And then I'm going to jump down to part D. I'm going to have you fill in the other two before you hand it in at the end of the semester. But in this one, the slope would be what's in front of that x, which really, there's a 1 in front of the x. Whoops, I covered it up. There's a 1 in front of it and then divided by 3. So our slope is really 1/3. And our y-intercept is at 5/6, but again, it's an ordered pair, 0, 5, 6. Okay, so likewise now, let's just look at a couple examples of a horizontal intercept. So this is another, same thing as finding an x-intercept. Okay, so what is the initial value? Let me just draw a little graph over here on the side. If I had something like this, a line like that, and we'll extend it. Oops, that was terrible. Sorry about that. But this is right here is our vertical intercept. And this right here is our x or our horizontal intercept, so it's where it crosses the x-axis. So in order for us to find it, we are, instead of plugging 0 in for x, now we're going to plug in a 0 for y. Okay, so on this one right here, consider that equation y equals 2x minus 10. So if I were finding the intercept for that, whoops, the x-intercept, I would plug a 0 in for y, and I would write it like this, and then I would solve it. So I would end up getting x equals 5. Notice I'm getting an x value, whereas up above with the y-intercept I had a y value. So this would be the ordered pair 5, 0. When x is 5, y is 0. A couple more examples of this on the next slide. Let's see. Oh, okay, so that was the work that we just did, solving that. So if you have two intercepts, okay, this one we knew the y-intercept in this equation right there was negative 10, so that's the point 0, negative 10. And if we just found the other intercept to be 5, 0, if I take those 2 points, I have my graph. Okay, so that's what they just did right there. So let's find the horizontal intercept for the one we were talking about originally in the car problem. We know the vertical intercept is at 20,905, but now I'm going to plug in 0 for v. And now I have to solve it for n by bringing over the 20,000 and then dividing by the negative 1750. And I'm going to end up getting, it says not come out whole, but I'm going to end up getting n is about, when you round it, 11.9. So what does that mean? Because this would be the point 11.9 comma 0. Okay, so that's where it's going to cross the x-axis. So if having a 0 in for x means no years have gone by and the value is 20,905, this is kind of the opposite. This means at 11.9 years, the car has lost all its value. That means the value is 0 after that many years. Okay, so if you remember correctly on the graph, this is just a really rough sketch. We didn't have it all the way down to the bottom, but this would be that 11.9. That's how many years it takes for the car to be worth nothing, whereas this up here is when the years are 0, and that's the initial value. I'm going to skip over this Celsius problem, and let me just check this one. If there's anything I want to do on that. Okay, the only one thing I want to do is at number 12. They're talking about zeros of a function. Zeros of a function, the value of a function is really its y. Okay, we say the value comes out a certain way, it's y value. So zeros are when y equals 0. Or in other words, f of x equals 0. So they want us to find the zeros of this, which really just means I'm going to plug in a 0 for f of x. It's the same thing as finding an x-intercept. Okay, so if I solve that, I bring over my 9. Doesn't come out whole, but that's okay. I'm going to write it as 9/2. Okay, so that would be one of the zeros. Okay, if I were graphing that, that would mean that this graph, this function, crosses through the point 9/2, 0. And that's where it's going to cross the x-axis. So this is the same thing as finding an x-intercept. So there's some more practice exercises. Is a really great summary. You're going to find a couple really good summaries on Blackboard for these activities as well. So check them out and let me know if you have any questions.